Hey everyone, I'm Venkat from Sri Venkateswara College of Engineering, Bangalore, from CSE department. Today, along with my team, we have been gonna handling the topic basic traffic control system with priority scheduling and binary search tree, which is a mini project. And my team members are Rachan Gowda, Yashwant, and Vishnu. Now, I'll be gonna be giving the introduction for this topic and even explaining the role of data structure in this topic. Now let's go through the introduction. A traffic control system, it is essential for managing the flow of vehicles at intersections, reducing congestion and ensuring safety. Integrating priority scheduling and enables the system to process higher priority traffic such as emergency vehicles or high traffic lanes before others. This prioritization ensures critical traffic gets faster clearance while maintaining fairness. To implement priority scheduling efficiently, a binary search tree is utilized. Each traffic light is represented as a node in the BST where the priority determines the placement of nodes. The higher priority nodes are stored in the right subtree, while the lower priority nodes are stored in the left. This combination of priority scheduling and ensures dynamic and scalable traffic management. The approach can handle real-time additions or adjustments of signals while optimizing traffic flow for smoother and safer intersections. This model serves as a foundation for advanced traffic control systems. Now let's know the role of data structure in this topic. The structure. The role is the struct traffic light is used to define a traffic light object. It stores the properties which uniquely identifies the traffic lights and it gives the priorities to determine the importance of the light, which stays to represent whether the light is green or red based on the priority. And the binary search tree. The role of binary search tree is used to represent with node, struct node, which is used to manage the traffic light based on their priority. The left subtree holds the light with lower priority and the right subtree holds the light with higher priority. This makes it efficient to find and remove the traffic light with highest priority. And the primary goal of using binary search tree here is to ensure that the traffic light with the highest priority is always easy to find and manage by maintaining this ordering of light by priority. The tree traversal, the binary search structure always allows for prioritized processing of traffic lights in this program. The rightmost node of this binary search tree always holds the traffic light with the highest priority. Removing the highest priority light and updating the tree ensures that the next highest priority light is efficiently accessed. And the summary of benefits is the program is used as a binary search tree to sort and manage the traffic light based on the priority. Here, the highest priority light, the right contains the rightmost node, which always has highest priority traffic light, and it can be accessed or removed in O log n time. As the number of traffic lights increases, the binary search tree can continue to operate efficiently with logarithmic time complexity for common operations like insertion, removal, and searching. The binary search tree structure simplifies the management of prioritized tasks such as determining which light should have the green signal based on its priority.
Hello friends, myself Vishnu J. Currently I am going to explain the topic is the operating system OS plays a supportive and critical role in executing this program. Memory management, dynamic memory allocation. The program uses malloc to allocate memory dynamically for the new nodes of the binary search tree. The OS manages the allocation and deallocation of memory to ensure the program gets the required resource without conflicts. Example, the function malloc is a request to the OS for a block of memory. If insufficient memory is available, the OS will fail the allocation and return null. Process management. The process runs as a process and the OS handles loading the program into memory, scheduling the program to execute on the CPU, managing the program state transitions. Example ready, running, or terminated. I/O management, input and output operations. The program uses printf for output. The OS is responsible for directing the output to the appropriate device, typically the console. The library input-output library function, example printf, interact with the OS to handle these operations. Resource management, CPU allocation. The OS ensures the CPU is allocated to the program for executing based on scheduling policies. File system access, if required. Although this program does not directly involve file input-output, if extensions to save or log traffic light states are added, the OS will facilitate interactions with the file system. Times and delays, optional simulations. The program comments mention green light duration and red light duration simulations, which could involve delays if implemented. Example with sleep or system times. The OS manages these delays by tracking time and ensuring the process resumes after the specified interval. Summary: the operating system acts as a bridge between the program and the hardware resource. Its primary contribution include memory allocation and management, process scheduling and CPU time sharing, managing I/O operations and system call like printf, ensuring system stability and efficient resource usage.
Hi everyone, I'm Rachango TM. Currently, I will explain the topic about digital design and computer organization plays a supportive and a critical role in executing this program. Role of digital design: a binary representation. The program relies on binary representation for all data, example integer, states, and pointers. This is a core concept of digital design where the ID, priority, and state fields are represented as binary numbers. Logical decisions and comparisons, example in the BST integration and traversal, are implemented using digital circuits in the hardware, be a register and a memory, each variable or a structure. Example, traffic light node is stored in the register or a memory locations as guided by concept from digital design. The program indirectly manages these storage units through malloc and free. See control circuits, the conditional and iterative constructors in this program if file correspond to control signal and branching mechanics in the underlying digital circuits. This enables the decision making at low level in the CPU. Role of computer organization. Instruction execution. The program's C code is compiled into machine instructions that execute on the CPU. For example, the comparison of a live priority root highlight.priority translates to assembly instruction which the CPU processes using its arithmetic logic unit ALU. The malloc function and the pointer operations are translated into load store instruction interacting with memory. Processor design. The hierarchical structure in this program, such as tree traversal, requires the use of CPUs, programs, counter, register, and a stack. Function calls insert remove islets priority use the stack to store return addresses and local variables. Intermediate computations leverage CPU register for a speed. Memory organization: the dynamically allocated memory for the BST nodes is managed in this GUI, a section of memory managed by the OS. Variable like lights are stored in data segment or a stack depending on the scope and size. Summary: digital design and computer organization provide the essential framework for low-level data handling, binary representation, memory addressing and pointer manipulation, instruction processing, logical decision, and arithmetic comparisons executed by the CPU. Memory management, handling of variables in register, stack, and heap. I/O operations, facilitations of console output through system calls, Without the principles of digital design and computer organization, this program could not translate into the hardware executable operations required to run on a physical machine.
Hello friends, myself Ashwan. Today, now let us discuss the how the code works. The provided code simulates a traffic light control system using a binary search tree. Firstly, defining structures, traffic light. This structure represents a traffic light with three attributes. Firstly, it's ID, and second one is priority, and third one is state. ID is nothing but the unique identifier for the traffic light. Priority is an integer value indicating the priority of the light. State is an integer representing the current state, that is red for 0 and green for 1. Node creation and insertion. Now let us create a node called as new node. This function allocates memory for a new node and initializes its attributes with the provided traffic light data and sets the child pointers to null. Now let us insert the function using the insert. This function inserts a new traffic light into the binary search tree based on its priority. It works recursively. If the current node is null, a new node is created with the provided traffic light and returned. If the light priority of the new traffic light is less than the current node's light priority, the function insert the new node recursively into the left subtree. Otherwise, the function inserts the new node recursively into the right subtree. Removing the highest priority. This function removes and returns the traffic light with the highest priority from the tree. It also modifies a provided traffic light pointer to store the removed light's information. If the current node's right child is null, then the function copies the light data from the current node to the highest pointer, returns the left child, and frees the memory of the removed node. Traffic light control simulation. In this function simulates the traffic light control process using the binary search tree. It works in a loop. While the root of the tree is not null, it calls remove highest priority to remove the traffic light with the highest priority and store its information in highest priority light. It sets the state of the highest priority light to green and prints a message. Simultaneously, the green light duration is being placed. It sets the state of the highest priority light back to red and prints a message indicating which light is now red. Finally, it prints a message indicating that all traffic lights have been processed. In the main function, we create an array of traffic light structures representing the traffic lights with their priorities, calculates the number of lights in the array, initializes an empty binary search tree, loops through the light array, inserting each traffic light into the tree using the insert function, calls the traffic control function to start the traffic light control simulations. Overall, the code uses a binary search tree to effectively manage traffic lights based on their priorities. This is the output for the above code. The traffic light 1 is green and for the priority 3, and for the traffic light 1 is red for priority 3, and it continues for priorities 2 and 1 respectively. Thank you.